2500, this is, make it bigger, bigger and bigger. Let's say this is, again, these are initial guesses, so they not have to be, doesn't have to be exact. Again, there is a difference between a 50 and a 5,000. But between a 50 and 60, even a 50 and 100 is not a big deal. So I would say this is 2,500. Let's say they would be roughly here. So let's say 2,800. We take 2,800. So, oops. So let's say that C0, the real C0, not C0 star, let's say that is 2,800. Okay, so if we go back in the slide, okay, from C0 and C0 star, I can figure out Km. All right, so I just say that Km is equal to what? Is equal to, now I forgot, so it's is equal to C0, no, let me do that. I'm gonna see, oops, no. So I can see, I don't want to make a mistake. So I can see the equation here, all right? So Km will be equal to C0, C0 is this one, all right? So I click here, divided, open parentheses, ln of C0 star, that is this one, divided by C0. Close parenthesis 2 times, enter. So Km is 450, okay? What is Vm? So Vm, I'm going to look at here, Vm is equal to the, okay, so Vm will be the slope multiplied by Km. So I go back here, so this one is going to be equal to the slope multiplied by.
Did you have any problem with your water?
No, today no.
There was no alarm, right?
No.
The door was locked.
The door was
You
locked.
want to get it locked?
Oh yeah, we can unlock
Okay.
it. So Vm is equal to the slope multiplied by Km, we said, all right? And here we are. And are you sure? Vmax is equal to, yeah. And now we are left with V. The volume of distribution is going to be equal to the dose divided by C0. So the dose will be this one, so this will be equal to the dose divided by the real C0, all right? That will be this one. And I find the volume is 11, all right? So these are now my initial estimate. So I go back to Phoenix, let's put it here so I can see it, or I can write on a piece of paper, all right? So I go back to Phoenix, and now I have all the, it's the same drug, so it's going to be the same enzyme that is responsible for the nonlinearity. So it's very likely that the volume of distribution, Vm and Km, are the same. I don't have to re-estimate for every data set, all right? I can just use the same. So V, we said, let's say that is 11, all right? I don't have to go by all the digits, all right? It's just an initial estimate. Vm is 320. Km is 450. And now I can do the trick, all right, I fill down, it's going to be the same for all of them. So I have done with the the unit would be liter. I don't know if you let me do it. No. Anyway, we know that is the unit you need to keep track of it. All right. At this point, let's see what happened. I run. Let's see what happened. I'm gonna go to see, first of all, the graph. Where is my graph? Okay. I wanna see on the Semalog paper because that is easy for me. Okay. All right, this one is good. All right. That is the lowest dose. Then this one, it's okay. It's a little bit off. Okay. So what I did, I forgot to put the weight. I would say that if we put the weight 1 over y, it's more likely to be, this little over C of poor estimate of the lowest concentration, it might go away. So let's run it with the weight. Okay, doesn't change. We know why the lowest dose doesn't change. Because it doesn't matter, this is the linear dose. In here the kinetic is linear, all right? And then this is, I gained something. You see the fitting is better. All right, so I would say, also note, maybe you, if you remember when we used the compartmental approach, the blue line, the line of the predicted was always smooth, all right? What we see here, can you see that the blue line is a little bit choppy, is, this is because the differential equation is solved numerically, because you don't have an integrated equation, all right? But it's good enough, it's good, again, what we can do. It must be good enough, because we have no choice. So we can look at the other thing now that let's say the residual are scattered, all right? And again, these are data generated by me, so are very, good data. The parameters, let's look at the CV percentage. The CV percent, you see that for the lowest dose, the CV percentage is high. But of course it's high because, again, the kinetic is linear, so the CV percentage of VM and KM is a kind of big, all right? But it's expected because that is overdone for the low dose, all right? Let's check another good thing is, you see the volume of distribution is similar, is 10.9, 11.7, 11.9. The KM and the VM are similar, not identical, but close enough. So I would say that we have done, all right? So what we're going to say is that the kinetics, when I look at the homework, all right, you tell me, do you plot the data? From the data you observe that the kinetic is nonlinear. Therefore, you're going to do the Michaelis method. One thing, how would you know if it's one compartment or two compartments? This again, you would go back to the Gibaldi book, but if we